To start our studies of extrasolar planets, I want to start off with what I call comparative planetology. So this is simply comparing planetary features. So for example, we're looking at Mercury and Jupiter. So if I asked you which of these planets has an atmosphere, what would you say? You might notice that you don't see a surface on Jupiter. Instead, you see these wispy cloud layers. On Mercury, you see a lot of cratered surface. So from this, you might be able to compare these two planets by saying, well, it appears that Mercury either has no atmosphere or a thin enough atmosphere that you can't see it. And the fact that it's heavily cratered, the surface, implies that there must not be much atmosphere for the meteors to burn up in before they hit the surface, whereas Jupiter has such a thick atmosphere that we can't even see to the surface. What about these two planets? Which of these is Earth-like? Which of these is Jupiter-like? By looking at these types of images, we can start to make some kind of conclusions about the planets that we see. If you looked at these two planets, what would you say? Which is Earth-like? Which is Jupiter-like? What are the features that make you think one planet looks more like Earth versus another? Are you thinking about the atmosphere, the surface composition? This is part of comparing the planets. So one of the specific ways that astronomers can compare planets is by looking at the chemical composition. We use a tool called spectroscopy, which can measure the elements and molecules in the atmosphere of planets. This is a tool that allows us to determine the fingerprint of the elements contained within the atmosphere of other planets. When we see the absorption lines, which are these little dips here, these are the absorption lines that correspond to certain elements within the atmosphere. And when we know what those absorption lines look like from testing those elements here on Earth, and we compare them to the absorption lines of atmospheres on another planet, we're able to determine what those planets' atmospheres are made out of. You know that the Jovian planets are made up of lighter elements, right? Those gases, okay, maybe those metallic liquids, okay? And we know that temperature plays a major role in this. We know that the terrestrial planets are closer to the sun, therefore they're hotter. And when gases heat up, those atoms and molecules move faster. And if they move too much, they can escape, and no atmosphere can be contained on the planet at all. So when we compare our terrestrial planets to our Jovian planets, one of the main reasons that the Jovian planets have thicker atmospheres is due to the fact that they are technically cooler because they are further from the sun. So let's take a look, not only in terms of having thick atmospheres, but in terms of the type of gases that can actually be held closer to the planet. Terrestrial planets tend to have heavier gases such as carbon dioxide, nitrogen gas, and oxygen, whereas the Jovian planets can actually hold on to even lighter gases such as hydrogen and helium. So to give you an example of this, let's take a look at how gases move. So here we have a box of gas. Notice that these are like, let's say, hydrogen atoms moving around at cold temperatures, like out in the outer regions of the solar system, such as locations of Jupiter or Saturn or Uranus or Neptune. You can see that the gas particles are moving around very slow because it's very cold. When the gas particles are not active because it is cold, the gravity of the planet can hold onto these gases a lot more easily, allowing those thick atmospheres of hydrogen and helium. As we get to the inner parts of our solar system, it gets hotter and hotter. So I'm going to change the temperature here and make it very hot. And notice now that these gas particles are whizzing all around, they're moving, they're bouncing. This energy and the motion of these particles makes it hard for a planet to hold on to these particles gravitationally, which is why we don't see these lighter elements in the atmospheres of the terrestrial planets. So another way we can look at comparing planets, instead of via the atmosphere, is by the surface. And craters are a great way for us to look at the surface of planets. What we have found is that the smaller the terrestrial world, the less internal heat it is likely to have retained. Because remember, all the planets formed as bodies of accretion of smaller materials. So at one point, all the planets were this molten liquidy ball that slowly cooled off after it formed. But some planets still hold on to that internal heat. Our Earth, for example, is still active in the center. So what we've noticed is that the terrestrial planet is small and it can't hold on to that heat anymore. It doesn't have much motion on the surface. What I mean by motion is things like geologic activity, plate tectonics, and so forth. Our Earth has a molten interior, meaning we have plate tectonics and we have a lot more geologic activity on the surface. So therefore, when a meteor strikes the Earth, and turns into a meteorite, and it causes an impact crater, the Earth can renew the surface of that impact crater and essentially erode it away through internal heating mechanisms such as plate tectonics or volcanic activity. Now, in addition, the Earth also has a thick atmosphere, which also helps with the erosion. But let's say, for example, we look at the moon, the image on the left over here. The moon does not have an atmosphere, and it's a cooled off terrestrial body, meaning that there's no internal heat inside the moon anymore. There's no resurfacing of the surface. So craters on the moon stay, and there's nothing to erode that material. We see another crater example over here on Mars. Mars has a lot of atmosphere and a lot of wind, so resurfacing can take place on Mars. So this is another way that we can compare the planets. Now, if we want to talk about how old a planetary surface is, the easiest way would be to take rocks and do radioactive age dating, right? To actually get a real number age for the rocks on the surface. That's not always plausible because we haven't actually visited all the planets or definitely haven't bring back samples to do radioactive age dating. So another way that we can look at the age of a planetary surface is by looking at cratering rates and how craters land on top of each other and get some kind of relative age of surface features. In terms of geologic studies, this is called the law of superposition and cross-cutting. So the very basic idea of the law of superposition is that older material is at the bottom, while newer material is at the top. So therefore, if you have new craters forming on top of old craters, you know that the newer craters are newer and the older craters are older. Now, I said that a little silly, but effectively, if you have a cratered surface like the one in the image here, this big crater, it formed first because it had to exist there before this little crater here landed on top of it. So we know in terms of relative ages that this big crater here had to exist first before this little crater could land on top of it. I could also say that this crater is most likely younger than the big crater, and that this crater is most likely younger than the big crater because both of these land on top of this crater. In fact, this one even looks like maybe it had some material flow down into the bigger crater. I would not, however, be able to tell you which crater is older between this top crater and this bottom crater because there's nothing to overlap in terms of superposition or cross-cutting, so I wouldn't be able to tell you relatively which crater is older. So let's see if you've got this. Take a look at these three craters. By looking at the principle of superposition, you should be able to say which craters are younger and older. So you can see that crater 1 is partially covered by crater 2, so crater 1 is older. Crater 2 is partially covered by crater 3, which makes crater 2 older than crater 3. By inference in this case, you could say then that crater 1 is the oldest and crater 3 is the youngest. That is the basic principle of superposition. Cross-cutting relationships is the idea when any kind of feature cuts across an older feature. So the crater shown in this image, is older than the fracture or the crack that cut through it, because the crater had to exist first before this crack could go across it. So these are ways that astronomers or astrogeologists can do relative age dating of the surfaces of different planets. So let's take a moment to think about this. For this conceptual question, which planetary surface is newer, quote unquote, the surface of the Earth on the left here, or the surface of Mercury on the right? So consider cratering rates and erosion. So pause the video and think about it for a second. All right, hopefully you answered Earth because you don't see as many craters. Therefore, the Earth is renewing the surface, and we would consider that surface as newer than that of Mercury. Okay, let's check your understanding again. So based on the two relative age dating principles, that cross-cutting relationship and that law of superposition, can you write out the relative ages of the features in this image of a planet? Okay, so you see you have a crater here. Okay, that's crater A. We have crater C and crater B. So which is the oldest feature, which is the youngest feature, and explain your answer. And then say which principle did you choose to use to answer this question. So pause the video, write it down on a piece of paper, and then play the video again when you're ready for the answer. All right, so the oldest feature should be A, because C and B are on top of that feature. So A had to come first. Then we can see that C is slightly overlapping on top of crater B. Okay, so C must be the youngest. Okay, and then the in-between age is B. And for this image, the law of superposition was used. Another way we can compare planets is by looking at the magnetic field. The magnetic field of planets gives us a clue to the interior state of a planet. And this is more direct than looking at cratering rates. Cratering rates, if we see a lot of craters, it means that the surface is not renewing, and therefore it probably has a solid interior. If we see that the surface doesn't have too many craters, meaning that the surface is renewing, it would indicate that the interior is molten. But if we want to get more of a direct clue about the interior state of a planet, we can look at their magnetic fields. From what we have found is that if no magnetic field is found, it's most likely that the interior of the planet is solid. And if a magnetic field is found, it means that the interior of the planet is most likely molten. So a planet or a moon with a global magnetic field has some kind of liquid material in its interior that conducts electricity and is in motion, generating either what we call a dynamo or a magnetic field. So just for example, here are a couple of planets with magnetic fields. We have Earth, Jupiter, and Uranus. Notice that what it takes to produce a magnetic field is some kind of liquid material that's also moving to have some kind of electric current. Now on Earth, this liquid material, okay, is a liquid mantle of rock and iron. But not all planets have that, right? So Jupiter has a liquidy material of liquid metallic hydrogen. And things like that can also produce a magnetic field. The only material that's not going to produce a magnetic field is if it's a solid body, such as solid inner core of iron. That would not produce a magnetic field. So when we look at magnetic fields, this is one of the ways we can have a clue about possible habitability of extrasolar planets, which are planets outside of our solar system. If we see that an extrasolar planet has a magnetic field, that gives us a clue to the fact that the planet may have a molten interior. If we don't see a magnetic field, we are able to conclude that it most likely has a solid material, a planet that has most likely dried up, and is most likely no longer habitable the way we understand life being need in terms of having magnetic field and plate tectonics for stabilizing the climate of the planet.